Now we want to wrap up our discussion of ice tables and talking about ways that we can make the math easier for us while still getting good answers. Determine equilibrium concentrations if both reactants are initially at 0.2 molar. I have CO plus Cl2 becomes CO Cl2, and Kc is 3.8 times 10 to the negative 10th.
All right, so whenever we see that we want equilibrium concentrations, especially when you're given initial concentrations as well, that's a surefire sign we want to be using an ice table. All right, so my equation that I'm going to use, or the chemical equation that's there, this is carbon monoxide plus some chlorine makes this CO Cl2 gas. So ICE. So 0.2 is both reactants. We don't want to miss that. Both reactants are at 0.2, 0.2. Not everything. I want to be sure it's not everything. There's nothing for information about COCl2, so we do want to be really mindful of that. I'm going to really read that carefully. The reactants are at 0.2. Presumably everything else is at 0. So if there's a 0 on the COCl2, that means we have to shift in this direction to the products. So that means we have to shift away from the reactants. So all the reactants will be negative, all the products, only one, will be positive. Coefficients are 1 on everything, so we just put an x across the board, minus x, plus x. Combine those, so equilibrium here, 0.2 minus x, 0.2 minus x, and x. Okay, so from our ice table, we've got that the concentration of COCl2 at equilibrium is going to be x. The concentration of CO at equilibrium is going to be 0.2 minus x. And the concentration of Cl2 at equilibrium is also 0.2 minus x. So if we had x, we'd be good to go. So what we're going to do, in order to solve for the value for x, we'll plug it into our Kc expression. Yeah, Kc. And so Kc is equal to concentration of CO, Cl2, concentration CO, concentration Cl2. So plug those in and we get, what, x on top? And then on the bottom, they're both 0.2 minus x, so the bottom is just 0.2 minus x squared. Okay, so overall, we have this equation. All right. So right now, when I look at this, I have an x to the first power on top and an x squared on the bottom. That means I would need to use a quadratic equation to solve for this, x. In general, I want to avoid doing that. One, it's a pain. It's a long time. It takes a long time. It really adds a lot of work. And I really don't want to do it. And so, plus, it's also not necessarily a good idea because there's a lot of steps to it. There's a lot of arithmetic in using the quadratic equation. You have to go through all the negative b plus or minus square root of b squared minus 4ac all over 2a, right? You got to do it twice for the plus and the minus. You got to get that number out. You got to check both of them to see which ones are possible. It's just, you really open yourself up. The more steps you do, the bigger the issue will be. Especially because you'll know this Kc, which is part of the equation, is this number right here. That is a very low number, 10 to the negative 10th, which means it's going to make the arithmetic and using the quadratic equation really difficult. It is very, very error prone. It's a hard calculation to get right. So we can also see that Kc is very, very low, right? This is a very small number. So what that means is this ratio right here, the top of this fraction is probably very small. We would say that this is a very reactant-favored equilibrium. So yes, you have mixed carbon monoxide and chlorine, and they will potentially react to make COCl2, but not a lot of it. We would not expect that this value for x is going to be very small. In general, it's just not really going to change. So what I'm going to do is I'm going to make an approximation. My approximation in written words would be that x is small. X is much smaller than 0.2. So you'll note I have a double less than sign, means that it is a lot smaller. So what that means is I'm going to approximate, this is an approximation, this is true. I'm going to approximate that 0.2 minus x is basically just 0.2. So if you think about it, if you have, say, $1 billion and you give away 1 cent, you still basically have $1 billion. Because $1 billion is a lot bigger than a cent. So if I'm doing 0.2 minus x, because x is really small, which I can tell because of the very small value for the equilibrium constant, 0.2 minus x is just basically 0.2. So I can make the approximation here that 0.2 minus x is 0.2, and I can take this and substitute it in right there. What that then simplifies my equation greatly to being Kc is equal to x divided by 0.2 squared. Because 0.2 minus x is basically 0.2. This becomes much simpler because now x is equal to 0.2 squared times Kc, which would be 0.04 times the 3.8 times 10 to the negative 10. I just plug in the Kc value, and from that I get, where to go? X is equal to 1.5 times 10 to the negative 11. So using the approximation, it takes some work to set up the approximation. I hope you believe me when I say that this is much shorter, though. After you make the approximation, the work becomes a lot easier than having to use the quadratic formula. You will note we don't approximate the x. You don't say the x turns to 0, because the only reason why an approximation works is in addition and subtraction. When you add and subtract two numbers of very different sizes, the answer is very close to the really big number. If you have $1 trillion and you spend one more, you get $1, you still basically have $1 trillion. It hasn't really changed a whole lot. But when you're dividing out, it can matter a lot. The magnitude is still, if you have two very different orders of magnitude, it still matters. So it's only in the subtraction and addition that we would make this approximation. So we can get this out. If you are going to use approximation, it makes the math a lot easier. You avoid doing the quadratic equation, which you should always do. Or also in the case we have like a third power or like a fifth power here, lots of high powers, you can't necessarily use an equation. There's a cubic equation, there's a quartic equation, there is no fifth power equation, and so it becomes hard to do. And so you have to use fancier tricks to solve these problems. So approximations are always your friend. And so definitely want to use an approximation here. And so we can use this and take it. The thing is, we do have to check our work. We can't just willy-nilly be making approximations. We approximated that 0.2 minus x is 0.2. We want to check to see if that is valid. So whenever you make an approximation, which you should do whenever you can, you got to check it. And so what we want to look for is we're going to do change divided by initial times 10. I'm going to get a percent, and I want to make sure that's less than 5%. So when I say change and initial, I'm talking about up here. I'm talking about from the ICE table. We approximated basically that this change, x, was much smaller than 0.2, and our cutoff for much smaller is going to be 5%. And so what we can do is take our change, which was just, this is x divided by the 0.2, multiply that by 100. So x is 1.5 times 10 to the negative 11 divided by 0.2 times 100 to turn this into a percentage, and we get 7.6 times 10 to the negative 9%, which is good. That's a sign that this is very small. This percent change was very small, so you know our approximation that x 0.2 minus x, which is 0.2, this is the error of it. The error is you're dealing with a 7.6 times 10 to the negative 9% percent error, which is not error that's ever going to matter. Not quite done though, right? What we wanted, we have X, we want equilibrium concentrations. So if we return to, we had that the concentration of CoCl2 at equilibrium would just be equal to X. So it is the value 1.5 times 10 to the negative 11 molar, not a ton. The concentration of CO at equilibrium was going to be 0.2 minus X. So that is 0.2 minus 1.5 times 10 to the negative 11. So that gives me, if I evaluate that, 0.1, that's 9 nines, 85. So this is basically what I'm saying when I say that this is 0.2 minus X, that's basically just 0.2, because we do have to round this, right? We got to round it to sig figs. Your addition and subtraction will say this number of digits after the decimal point, so 1 here. So if we round that, we get 0.2 molar. Yes, it is technically a different number, but that number is not distinct enough from 0.2, and especially with respect to rounding, right? One of the ways you can also think about this, our input number only had one sig fig. It was 0.2 molar. That's not very precise. Subtracting this hyper precise number is not going to be noticeably different. So we get 0.2. Similarly, the concentration of Cl2 was 0.2 minus X, and that just becomes 0.2 molar. And so this is what we mean when we say that you can do these approximations. So you need to always check your approximation. I think that, doing the math with the approximation, which is much faster than the quadratic formula, and checking the approximation is always going to be faster than just, brute force doing the quadratic formula. If this number was greater than 5, you would need to do it anyway. You can't use an approximation method, but it really makes your life a lot easier to use that approximation method, and I encourage you to use it when you can.
So we see with a really small value for Kc, right, 10 to the negative 10th, this is a very reactant-favored equilibrium. Basically, if you mix CO and Cl2, not much CoCl2 is made, right? You don't really get a lot of it. Very little of it is there. Your concentration, you can see here, is tiny, 10 to the negative 11 molar. But the thing is, CoCl2 may have very, very, very low concentration here, but that's called phosgene, which is a chemical weapon. And so this is a really, really dangerous chemical, and even a little bit of it is a very bad thing. So we want to be really mindful of it, that yes, this reaction really doesn't happen. You don't make a ton of CoCl2. Almost all, to many significant figures, your initial concentrations of reactant isn't totally unchanged. But it's important to note that you have made some product, and that product is dangerous. And so this is something that we really need to be mindful of. If you're going to be working with carbon monoxide and chlorine, which are already extremely dangerous, you could be making something that's very, very potent, and something that we really want to be mindful of. That this would just happen passively. Some will be created, not necessarily a lot, not necessarily, that there'd be a ton of it there, but some will be made. And that's something we really want to be careful of. And it's important to be mindful of when we're just mixing chemicals together or storing chemicals together. This approximation method is generally something we want to be using. The approximation will almost always make the math easier, and if it makes it fewer steps, if you're trying to use the quadratic equation, especially with a Kc like that your A, B, C values start to become really small numbers, which can just be difficult to work with, and really leads to the increased chances of making a mistake. So yes, you are making an approximation, but because you make the math fewer steps and generally just a more simple process, you are less likely to make a mistake in doing that math. So it's always a good idea to try an approximation and then check whether or not it's valid, right? And our cutoff is going to be if it's less than 5% of that initial concentration. So we are going to be pretty aggressive with when we make approximations. You can just, in a worst case scenario, you use the approximation you see and you reject it. Then you just go back and do the quadratic formula. The quadratic formula is always going to take you like 20 times longer than the approximation, so you haven't really wasted a ton of time. So with this together, we can kind of put an overall strategy for when we're dealing with ice tables. You know, you set up your ice table. First, you look at the reaction and you figure out what shows up, which of the compounds or substances shows up in Kc or Kp. You don't need to worry about solids, liquids, right? Get those initial concentrations. Figure out the direction of the shift. Look for things that are missing initially because it has to shift to replace that, or use your reaction quotient. Then, you know, you get your E value, and then it becomes, you take the whole point of the ice table is to set up those values of X and plug them into Kc. And then you just try to solve for X. So, you know, at the bare minimum, you can try to isolate it. We set up some reactions. The first couple examples we looked at were designed in such a way that you could just solve it algebraically. Otherwise, if K is really big or really small, try to use some approximations to solve it using square roots and stuff like that. Otherwise, quadratic formula. You know, you can always do that. It's always a possibility. And then you can always check your answer at the end. Is the Kc value consistent with the concentrations you got? You're saying these are the equilibrium concentrations. Do they combine to give you the Kc value that you started with, or that was given to you, or Kp value, whatever the equilibrium constant is? Participation 220, question 3. An initial pressure of 0.53 atmospheres of carbon monoxide is placed in a box. What is the partial pressure of carbon dioxide at equilibrium? Reaction is 2 carbon monoxide becomes carbon and carbon dioxide. Kp for this is 1.2 times 10 to the negative 6. This is the third question on participation 220, due Friday, February 20th at 11:59 p.m. over on Blackboard. Link to the assignment is below the document where these videos are posted. Again, an initial pressure of 0.53 atmospheres of CO is placed in a box. What is the partial pressure of CO2 at equilibrium? Reaction is 2 COs becomes C and CO2. Kp for that is 1.2 times 10 to the negative 6.
That's it for chapter 13. So all about chemical equilibrium, you know, kind of ending here heavy on the ice tables with the calculations, but we also want to go back and be able to do defining chemical equilibrium, you know, distinguishing Kc, Kp, those equations for just the equilibrium constant, all the shifting, Le Chatelier's principle, that more qualitative kind of stuff. And then the ice table calculations as well.
That's it. 3 questions on participation 220. You want to find all 3 of those questions, get them answered, and get those answers submitted over on Blackboard by Friday. Week 6 homework covers both sets of videos. Chemical equilibrium post lab is due Sunday. Otherwise, that is going to be it for us this week. That's it for chapter 13. Also, we'll start chapter 14 next week. All that's left is the answers for participation that go live on Friday night. Otherwise, enjoy the rest of your day, your weekend. I'll see you next week. Bye-bye.